All right. Hello, everyone. Thanks for attending my talk. I'm Antoine, and I'm a software engineer at Datadog, working in one of the infrastructure groups that takes care of service-to-service communication. And I'm going to talk about our experience adapting an existing xDS control plane from built for Envoy to gRPC. So just a few words about the company. We are an observability product with a bunch of sub-products and integrations. You can check it out. We have a fairly large user base, which means that we have a sizable infrastructure to support it. I'll start with a little bit of background on what is service discovery. So in its simplest form, service discovery just turns a human-readable name into a list of IP addresses that networking applications can then use to connect to a service. And by far, the most common way to do service discovery is to use DNS. DNS is an old protocol. You give it a name, it gives you an IP address or a list of IP addresses, and it's supported by most infrastructures. An alternative to that is to use xDS. xDS is an API originally created for Envoy, and it has a very rich set of features. So in a way, you can think of it as a replacement for DNS with a lot more features. So in the last few years, gRPC added support to do service discovery directly through xDS. How do we do service discovery at Datadog? So historically, we've been using the cloud provider DNS APIs to provide cross-cluster information in our Kubernetes infrastructure. There's no really blessed built-in way to do cross-cluster discovery. The way it works is that there are some processes that write all endpoints that are spawned in the Kubernetes clusters, and we wrote them into the cloud provider DNS API. This worked, but this had two main problems. One is that when a large number of pods were created in a short period of time, we would start to get rate limits, and this would make the propagation time kind of unpredictable. And for some client applications, you don't really control when they are going to be resolved from DNS. So here the baseline for endpoint propagation was really the problem that we were trying to solve, because it slowed down deployments, and in some cases it even caused some outages as the DNS information was just out of date compared to what was happening in the data centers. So in order to solve these problems, we replaced the cloud provider APIs with our own data store. This works around the API rate limit that we were hitting, and it gave us predictable endpoint propagation time. And in addition to that, it also gave us the opportunity to start customizing the serving path. And so, for example, we started storing the availability zone of each endpoint in addition to just the endpoint IP address. And it started letting us serve more interesting queries, such as give me the endpoints in my availability zone, which can cut on cross-AZ costs, like cloud providers typically charge for that. And finally, this lets us start experimenting with delivering the updates through a different protocol. In the case of Envoy that we used for standalone proxies, this meant xDS. Next slide, please. Yeah, okay. How does that impact endpoint propagation time? So DNS has a pool-based model with caching at various layers, and when to resolve is left to the application. In the case of gRPC, we re-resolve whenever a TCP connection is closed. That's a reasonable behavior to have, but it's not the best within the data center. xDS, on the other hand, is a push-based model. So the control plane decides when to send updates and when data planes are going to use the new IP addresses. So that should give you faster propagation time, right? Well, it turns out that when there are a lot of endpoints churning, which typically happens in deployments, sometimes we have tens of pods rolling at the same time. If you're pushing every single update, you're going to burn the control plane and the data plane. They're going to start doing a lot of work. So you have to introduce some form of batching here in order to make that more efficient, which introduces a new delay. So with this batching in place and the rest of the overhead in the system, we landed in an order of 20 seconds for propagation time. So how does that fare against DNS? Well, because we control the whole DNS stack, we were able to set really low TTLs, and we were also able to roll out some custom resolvers for gRPC, which poll every 5 seconds. So in the case of DNS, for us, we also ended up with propagation times that was actually quite acceptable, like a bit longer than xDS. So I'm mentioning this because when I talk with folks that are looking at implementing xDS, I often get faster propagation time as like an advantage. In our case, that wasn't really a key benefit. So let's talk about the real benefits of using xDS over DNS now, which is the data models that xDS provides. So A records in DNS have very simplistic data structure. There's only so much an application can do with that. On the other hand, xDS gives you a much richer data model. You can start grouping endpoints by locality, give them priorities, weights, and metadata, and stuff like that. And then there's also a bunch of other resources that you can deliver through xDS that lets you configure other aspects of data plane load balancers. And in order to configure those more advanced aspects, we built our own internal APIs that kind of resembles the Kubernetes gateway APIs, for those that are familiar with that. And we use that mostly for our standalone proxies. This lets us leverage some features of Envoy, like the automatic failover that prefers the local zones and will only use endpoints in other zones when there are failures in the local zone. We also use that for configuring routes, which is like a very typical thing to do for a reverse proxy. You definitely want to have that on a self-serve basis for your users. We also use it for sharding in some places. The idea here is that you look at the content of the request and you will route it to the right endpoint depending on what it contains. And we also use things like endpoint weights, and one of the main use cases for them is overload testing. You ramp up the weight of a single endpoint until it shows signs of overload, and that will kind of give you a baseline for what a given server can handle. All of these features we use with Envoy. So I'm still talking about Envoy here, just to be clear. The common theme for all of these features is that they require changes in configuration at runtime, so you definitely need some form of control plane for this. So envoys are not the only place where we do load balancing in our infrastructure, and in fact, we have a lot of gRPC applications, and they form the majority of places where service-to-service communication occurs. So our starting point here is we use DNS for service discovery, and lots of code and configuration that we bundle directly in applications. The first thing we tried was to replace the gRPC built-in load balancer with an Envoy proxy, sidecar. If you've been following the CNCF ecosystem, this is a very popular approach that is used by most off-the-shelf service meshes. And the idea here is simple. You run all of your traffic through local proxies that will take care of routing and load balancing. And we offer an approach like this for our teams internally. The advantage of this approach is that you get all of these features that we had for standalone proxies, like with no customizations to the control plane, basically. You get them for free. But it also comes with some drawbacks. The first one is UX. Because of the way Envoy is dealing with xDS resources, you kind of have to declare the dependencies of your service externally. And like for people migrating to our sidecar-based approach, that was kind of a major pain to actually list those. The second problem is that you have to allocate resources properly for your sidecar. This is like kind of a limitation of Kubernetes, but it's a very practical one for us. You have to allocate the right amount of CPU and memory to the sidecar. And so as you can see on the bottom graph, which is a heat map of like how much CPU the sidecar is using, there's no one size fits all. If you allocate too much, you will to all the sidecars, you're going to end up wasting a lot of resources across your fleet. If you don't allocate enough, then some applications will suffer because they don't have enough resources allocated to the sidecar. And another problem is that there is an inherent cost to a user land network hop. So this is a graph actually advertising the performance of Linkerd, which is in green. It adds a bit of latency, less than Istio, which is another service mesh. But the blue line is really, like, when you see that, for sure, this is the thing that you want your applications are going to want that. This is the baseline without a service mesh. So for us, it was, especially given that our system has like a kind of a large fan out, the requests tend to go through a lot of hops in order to be served. This was clearly not acceptable to roll that approach everywhere. So in many scenarios, this won't matter, but for us, it really mattered. We also found that people were generally less likely to successfully troubleshoot the system with the sidecar in place. And we've had engineers that tend to customize gRPC quite heavily, and that were also kind of bothered by the load balancing externalized because they couldn't get the same level of control that you get when you customize the load balancer in your application directly. All right, so sidecar approach worked for some users, is very useful in some specific cases, but really for a lot of applications for us, the cons clearly outweighed the pros. At the same time, our users really want those features that I listed before, so that brings me to proxyless. So the idea here is that instead of having sidecar source service discovery information from xDS, we connect gRPC directly to the control plane and get some of these features. It's very compelling on paper. In practice, it turned out not to be as easy as we thought. So the first set of changes that we had to make was to our control plane was to support the transport protocol that is used by gRPC. The transport protocol is how the control plane and the data plane communicate resources rather than what these resources contain. And so one of the specificity of how Envoy works is that on startup, it will go to the control plane and it will query for all resources that it needs. And it's the responsibility of the control plane to know what this specific Envoy instance needs. And this is also one of the reasons for this UX difference, these UX problems that we were seeing, I was mentioning before. So this is different from how gRPC works. gRPC will wait for your application to actually create some clients and send RPCs to them to lazily go and fetch the things that you need, which is actually very nice on the control plane side because you don't have to have knowledge of these applications. They will just come and ask for what they need. We had to change our control plane, which had this assumption that it needs to know everything about the nodes in order to properly deal with gRPC for this. Okay. Second problem that we ran into with the transport protocol was with the variant of the transport. So there are two variants of the xDS protocol. One is state of the world, which is older version. And another one is a newer, more efficient variant called Delta, where you don't have to resend all the resources for clusters and listeners. So I'm not going to get into details of what they are exactly. But the important thing is that gRPC only supports state of the world, and our control plane only supported Delta. So that was something that we also had to address. And here the problem really is that we use Go control plane, which is kind of the reference implementation of a control plane. And its implementation of the state of the world made a lot of assumptions on how Envoy works and was really broken when connected to gRPC. So we addressed all this problem. I mean, one of my colleagues, Valerian Roche, actually went and fixed all of this. It's available in our fork, which is public. He's also a maintainer of Go control plane, so hopefully those changes eventually make it in upstream. So another thing that we had to change was the configuration itself, and that was kind of expected. Envoy is a proxy, so we need to tell it, for example, what ports it needs to listen on and how to route requests to the right destination when they enter the proxy. gRPC is different. It's not a proxy, so it has a different kind of listener that is kind of a special listener that says that it's just a gRPC client. So that was a simple change to make. But it wasn't the only change. We also actually had to change a lot of resources because either gRPC implemented just a subset of the features that we needed, or it implemented it in a slightly different way. Or in the case of security features, for example, it would outright reject the configurations as we had it for Envoy because gRPC only implements a subset of these features. It actually doesn't accept to get a configuration that it doesn't understand. That makes a lot of sense to do that for security features, right? You don't want to ship a configuration to a data plane. It doesn't understand it, but it still tries to apply it. But still, it meant work on us to kind of like, ship configurations that was compatible with gRPC. So to summarize where we're at now with this work that has been done, so on the good side, we have a bunch of features that we were successfully able to implement, like the traffic shifting, per path and header-based routing, and ability to kind of centrally control what load balancers is used by each gRPC instance, by all clients. There's very solid cross-language support, actually, which was really important for us. Java, Go, and Python are heavily used internally. We have more and more JavaScript as well. While implementing that, the designs for all these features is very thorough. It's very good. The specifications are explaining how these features work in great details. As an aside, sometimes the hard part of reading the gRFCs is really kind of understanding the motivation for certain features. I mean, if you don't understand why you might need something, probably you just don't need it. But yeah. So you still retain the ability to use custom load balancers. This is something that was actually really important to us because we are rolling out some custom features there, like the PID balancer that Sergey talked about earlier today. On the less positive side, there's a lot of features that we were using in Envoy that are actually not implemented in gRPC. For example, we use a feature called over-provisioning for zonal failover, which gRPC doesn't support. So you kind of have to implement more things on the control plane here. We use load balancing subset metadata for sharding. If you're familiar with, those that have played a lot with Envoy might know about this feature. It's also another feature that is not available for gRPC. So the sharding stuff, we haven't yet adapted to gRPC. Endpoint weight is another example of a feature that is not yet implemented in gRPC. Another thing is that some features that are available through the resolver abstraction become inaccessible as you're using xDS. And they fall into two categories. One of them is those that are configured directly through the service config and that are not yet available through xDS. So you will kind of lose some features. I gave a few examples if you use xDS instead of a custom resolver. The other sort of features that you lose is the ability to set custom endpoint metadata. So if you're doing that, xDS, the protocol and the config has the ability to do that, but it's not actually available to a custom balancer that you use through the built-in support for gRPC xDS. So just to conclude, so there's inherent difference in the xDS transport that was not really a key benefit for us compared to DNS. It's really the data model that is important. Adapting our xDS control plane was actually quite a big effort, really, more than we anticipated. There's changes to the transport and then changes to the xDS resources themselves. The feature set is also quite different. This is clearly something that you need to research a bit. If you have an existing Envoy control plane, make sure that the features that you rely on are implemented on the gRPC side. This is some work. That was a large part of the preliminary work that we did here. And finally, you have to be aware that some of the customizations that you might be, if you're heavy on customizing gRPC, some of those customizations that you may be doing might not be possible when you switch to gRPC xDS. And that's it. I'll open it for questions.
Two questions. So the first is, just here at the end, you said that gRPC only supports the state of the world sort of mechanism for communication. Is that something that's inherent to gRPC, or could it grow support for the xDS?
So I think it can definitely have support for it. I will defer to maintainers. I think Eric is probably the best person to answer this question, really. Support for Delta. No.
We really like Delta protocol. We've looked at it multiple times. It's just that we look at the other things we're doing, and state of the world works. So it's mainly to have either the time or it being important enough to get to. But it's a much better protocol, and we still will have some hiccups occasionally with some details of state of the world.
So just to be clear here, for us, like the limitations of state of the world themselves were not really a problem.
Right.
I mean, it has everything we need. It's just that we, like when you start a control plane for Envoy,
Sure.
you start with Delta, right? Like that's the default now.
Yeah, state of the world is worse for Envoy than it is for gRPC, because gRPC is subscribing to fewer resources. The deficiencies of it don't show up as much.
Okay, so it's somewhere on the roadmap. You just don't want to make
Yeah,
a
it's just priorities and stuff. We'd love to have it if someone came along. It'd be fabulous.
Awesome.
We like it.
Okay. Can I ask another question? The other one was, maybe you said it at the beginning, but I didn't catch, is all the stuff that you're doing here, is that for your internal communication, or is it also for your customer traffic? And
Yeah, so I was wondering whether that would be obvious or not, but yes, that's all for internal infrastructure.
Okay.
Our clients communicate with our external load balancers using DNS.
Okay. Thank you.
So.
So you said that with DNS, you were getting like a 25-second propagation time, and then like with XDS, 20 seconds. What's the like actual cause? Or could you really get it conceivably down to 0 if you had all the data available, or are you really just trickling it down that slowly to the clients?
So are you asking what causes these 20 seconds for XDS? So I talked about the batching, so you kind of have to wait to accumulate some updates. You can just like immediately push anything that you get. It's just going to be too costly, I think. I mean, I'd be curious if you have other approaches that work, that cut down on but there's always this inherent trade-off between like trying to batch things and waiting versus like whatever you do, you always have this trade-off too.
Yeah, I guess, is the batching of 5 seconds determined by the client load, or is it determined by like?
It's somewhat arbitrary. You could possibly a smaller value would work, just like for DNS. Possibly a smaller TTL would work. It would cause a bit more traffic, and would be a bit more work both on the data plane and control plane. Maybe acceptable. In any case, like I guess the takeaway from this is that we were able to achieve a reasonable propagation time with both DNS and xDS in the end.
Cool, thank you.
I wonder if you potentially wanted to decrease this propagation time with gRPC workloads. Would it work, because gRPC has to just load and monitor a few resources?
So I don't think that would make a difference. I think we have some large workloads where currently we push all the IPs. We don't do subsetting on the control plane side. So sometimes you have like hundreds of IPs in there, and sometimes they change very rapidly. So yeah, whether it's gRPC client or Envoy client doesn't make a difference here. One more question, if there is one. Otherwise, we can all go to happy hours, I guess. No, there is another keynote. Happy hour later. Yeah, okay. All right, thank you, everyone.